In this lesson, we'll be talking about describing relationships between two categorical variables, recognizing and describing conditional distributions, and describing and recognizing Simpson's paradox. At times throughout this recording, you will need to pause in order to do some work and then continue on with the recording. Up until this point, we've concentrated on relationships where at least one of our variables has been quantitative. Now we're going to shift to talking about relationships between two or more categorical variables. Remember that some quantitative variables, such as age, can be turned into categorical variables by grouping them into classes. So the quantitative variable of age can be split into classes, for example, 0 to 4 years old, 5 to 9 years old, 10 to 14 years old, and each of those classes would then be a category, turning it into a categorical variable. One of the ways that we describe the relationship between two categorical variables is with a two-way table. A two-way table is simply a table of counts that's used to organize data about two categorical variables. When we look at a two-way table and summarize it, we're actually looking at two variables that will either be described in the rows, where you can see the row description, or the columns, where you can see the column description. In this case, our row variable is education. It talks about the different categories of education for our population. And our column variable is age, so it talks about the different categories. If you will turn to your book, page 241, and read the background information on 419, it will help you with this example. The row totals and column totals in a two-way table give the marginal distributions of the two individual variables. Notice that they are in the margins. So if I wanted to look at the marginal total of those who did not complete high school, I would follow it all the way across to the total and find that 27,853 people did not complete high school. That would be the marginal distribution. I could also look at this as percents, which is the way it is most commonly shown. And we would look at the 27,853 divided by the table total, 175,230. That would be a marginal percent. I can also have marginal percents for the columns. So if I wanted to know the total that were 35 to 54 years old, that would be 81,435. And I could turn this into a percent as well by taking the 81,435 and dividing it by the 175,230. That would be a marginal percentage. Marginal distributions can be given as either counts or percents. However, using appropriate percents from the counts often allows us to best describe the relationship between the two categorical variables. We're going to use this two-way table in order to answer a few questions. The first question that we'll look at is what percent of all people only completed 1 to 3 years of college? We have to pick apart this question to make sure that we can find the appropriate numerator and the appropriate denominator to figure out the percent. So our denominator will come first. What percent of all people? The denominator in this case is all people. And if I were to look at where all people are on this table, it would be the 175,230. So the 175,230 becomes my denominator. The numerator, as I continue on with my question, only completed 1 to 3 years of college. So I need the total that completed 1 to 3 years of college. That would be 44,445. So to find the percent, I would have the numerator, 44,445, divided by the denominator, 175,230. That would give me a percentage of 25.36%. Try the others on your own, so pause, try them on your own, and then come back and we will take a look at your answers. So the second problem asks us, what percent of people aged 35 to 54, there's our denominator, people aged 35 to 54. So our denominator is 81,435. Only completed 1 to 3 years of college, so my numerator is going to be 22,618. So if I divide my numerator by my denominator, I will end up with 27.77%. The next one says, what percent of people aged 25 to 34, there's my denominator, people aged 25 to 34. My denominator will be 37,786. Have completed 4 years of college. So 4 more years of college is 11,066, and I would divide 11,066 by 37,786, and I would get 29.29%. So I will move my graph over here so that you can actually see the calculations and check yours. The next problem asked me to make a bar graph to display the percent of people in each age group that completed at least 4 years of college. So when you do a bar graph, several things I hope you remembered. You must title and label your graph, and also a bar graph should have space between the bars. Otherwise, you're drawing a histogram. Notice that it says that I'm looking for a bar graph to display the percent of people in each age group. That means that my denominator is going to change for each bar. I'm looking for the percent of people 25 to 34 that completed 4 years of college. So that would be 11,066 divided by 37,786 for that bar. Then I'm also looking for the percent of people aged 35 to 54, total is 81,435, who completed 4 more years of college. So my numerator is 23,183. When I get to 55 plus, I want to know the percent of people 55 plus. So my denominator is 56,008. Have completed at least 4 years of college, which is 10,596. So if I do those calculations, then I will end up with a bar graph that looks something like this right here. And the percent of people in the 25 to 34 age range is 29.29%. Again, that's 11,066 divided by 37,786. In 35 to 54 age group, it's going to be 23,183 over 81,435. And for the 55 plus category, 10,596 divided by the 56,008. Now let's talk about conditional distributions. To find conditional distributions of the row variable for one specific value of a column variable, look only at that one column in the table. Find each entry as a percent of the total column. So we did a little bit of this when we put together our bar graph. Let's take a look really quickly, and we're going to look at education for the 55 plus crowd. So I'm only going to look at the 55 plus crowd. That would be this right here. And I'm going to try and find the education. So of the 55 plus crowd, the percent that did not complete high school will be the 14,224 divided by 56,008. The percent that did complete high school and only completed high school is going to be this number, 2060 divided by the 56,008, etc. down the way. So let's go ahead and write that in for the columns here. I have 14,224 divided by 56,008, which is going to equal, scooch over just a little bit, 25.4%. For the completed high school, 20,060 divided by 56,008, which is going to equal 35.8%. Likewise, for 1 to 3 years of college, 11,127 divided by 56,008 is going to be 19.9%. And for 4 more years of college, 10,596 divided by 56,008 is going to be 18.9%. Note that if you add all of the percentages in this column, they should add to be 100%, because we've now addressed all people 55 plus that were in our population. Now I'd like you to pause and take a look at the bar graphs on page 248 in your book. you'll notice that there are actually 4 tables there, or 4 graphs there. Take a couple of minutes and see if you can do a comparison looking at those 4 graphs. Note that it's not as easy as it was when we were looking at quantitative variables, where we could do a quick scatter plot and we had such numerical values as R, or correlation coefficients, to be able to help us describe it. Now you actually have to look not only within each of the graphs, but across each of the four graphs in order to be able to make comparisons. We'll take a look at this in class when we come back to class, but make sure that you've jotted down a couple of notes. Now I'd like to move forward to Simpson's paradox. Simpson's paradox refers to the reversal of the direction of a comparison when data from several groups are combined to form a single group. It's an extreme case of the effect of lurking variables. Well, that's a lot to be talking about, so why don't we take a look at a very specific example. I'd like you to turn to page 249 and 250 of your book and read through the example 423. So pause here and do that. After you have read it, come back and we'll talk a little bit about it. In the example, it talks about 2 different hospitals, Hospital A and Hospital B. And you're trying to make a decision, an informed, educated decision, about which hospital you want to go to. You notice that in the information that's available to you, at Hospital A, they had 2,100 patients in the time under study. And of those 2,100 patients, 63 of them died, and 2,037 of them survived. And so you looked at it and said, well, that means that 3% died and 97% survived. You then went and looked up Hospital B online to find out how they fared. And out of 800 patients, they had 16 patients that survived, or that died, and 784 that survived, or 2% died and 98% survived. Now there's a couple things you notice. One is Hospital B had fewer patients than Hospital A. Maybe it was a local community hospital as opposed to a larger hospital. But more important to you, you notice that the survival rate at Hospital B was higher than in Hospital A. So you decided you wanted to go to Hospital B. Well, a little bit more study might have indicated that you made the wrong choice. So if we were to take a look at the patients who were coming into Hospital A and the patients that were coming into Hospital B, we might find that Hospital A is actually treating a different type of patient. And based on the type of patient that they're dealing with, they may be unfairly biased towards the death rate that's there. So maybe what we find out is that Hospital A happens to have a trauma center. If they have a trauma center, they're flying in some of the worst cases from all over the state and all over the region to that particular hospital in order to be treated. That means that their survival rate could be going down because they had more people coming in bad condition. So if I were to break it down that way and look and see how many people were coming in fairly good condition, they were coming in for cosmetic surgery perhaps, or maybe they were coming in for something like tonsillitis or an appendectomy where it wasn't a critical case. These people were coming in fairly good condition. And if I look at the information about Hospital A and Hospital B for these patients coming in fairly good condition, the Hospital A only has 1% of them that died and 99% survived. Where when I look at Hospital B, 1.3% died and 98.7% survived. So in the case of those that were coming in good condition, Hospital A is actually performing better than Hospital B. If I look at those that were coming in bad condition, those critical cases, Hospital A had 57 come in, or 57 that died of the 1,500 that came in, which was a 3.8% of them died, where 96.2% survived. Where Hospital B only had 8 of their 200 died, but that was 4% of their people that came in bad condition died there, versus 96% of them survived. If I were to look at those coming in bad condition, again, from a death rate perspective, I would go to Hospital A, not Hospital B. So how can it be that I end up in a situation where Hospital A performs better for those patients coming in good condition and better when the patients are coming in bad condition, but yet overall, I'm looking at a situation where hospital A looks worse than hospital B. Well, that is because of a lurking variable, and the lurking variable is the condition of the patients. And what's happening here? Condition of patients. What is happening here is that hospital A is getting more of the difficult cases. So Simpson's paradox happens whenever we have more difficulty assigned to one person or one hospital or one category than another. And it causes us to have a situation where if we group everybody together, it makes it look like hospital B in this case is better than hospital A, but if we broke it out separately, we would find that A does better on both types. You might have seen something similar to this. Let's say you have a sibling, Susie. And Susie and you come from the same gene pool, so you're equally intelligent. But what you find is that you work a whole lot more than Susie does. So she doesn't have the same work ethic you have. Well, Uncle Johnny, your favorite uncle, has somehow come up with tickets to the state UNC game. And you want to go to it, but you've got statistics homework to do. And Susie starts bragging about the fact that she's finished all of her homework and she's ready to go. As a matter of fact, Uncle Johnny, take a look at my report card, look at all my A's, and look at my sister or my brother's report card. They don't have nearly as many A's in there. Well, overall, she's absolutely right. The number of A's that she's making are better than yours. However, what you'll find if you look a little bit deeper is that she's not taking the AP courses that you're taking. So if you look at non-AP courses on your transcript versus the non-AP courses on hers, you may actually have more A's than she has. And then if you split it up and put the AP category in there, and you look at AP courses in yours on your transcript and AP courses on Susie's transcript, yours may have more A's in the AP category as well. But overall, yours may not look quite as good as Susie's because you have more AP courses than she does. This is part of the reason that we have weighted GPAs rather than entirely unweighted GPAs. So don't let all the statistics fool you by rolling them all up together. It works in Susie's favor when they're all rolled up, but if you break it down separately and the colleges know the difference, then you're doing better because you're putting yourself into more rigorous courses.